Hi again, Math 215 students. In this video, we're going to be doing one last video for section 2.3. We'll be talking about invertible linear transformations. Now, as we start, here is our list of outcomes. As always, we're going to be defining what an invertible linear transformation is, and then we're going to be talking about the connection between these invertible linear transformations and matrices. We'll come back to this list towards the end of the video. To dive in, we want to recall a few things to prepare the way. We want to remember that when we first started talking about matrix multiplication, we talked about the composition of two linear transformations. Now that might be a bit hazy. You might want to go back and look at our first videos on matrix multiplication. But the idea was that if we're going to have the matrix A times B, and we're going to be multiplying that onto a vector, what we'd like to do is think of A and B as corresponding to linear transformations. When we take X and we multiply B onto it, that's going to take our vector X and multiply it to produce another vector in Rn. And then the idea is when we multiply A onto that, we'd like to imagine A is taking that vector, and whatever that vector is, A times that vector will be this vector here, A times the quantity bx. Now, we know how to multiply a matrix onto a vector, and that's all we've done in these two steps. But when we define what multiplication of matrices looks like, what we're shooting for is to find a definition of matrix multiplication that would take this vector x, and immediately, when I multiply by that product, produce the same result as the two steps, multiplying by b followed by a. Great, now that led to, believe it or not, our definition. And the way that it did, we've seen this slide before back in section 2.1. We kind of worked our way backwards from this expression, a times bx should be the same as ab times x. That was what we were starting with. That was what we were hoping for. And by interpreting the left hand and the right hand sides there, we kind of worked our way backwards. We said that a times bx, well, first of all, if we work inside the parentheses, we know how to multiply a matrix times a vector. We take the entries of the vector and we use them to scale the columns of the matrix. So that's what we were doing. Then a multiplies onto the result. And then when we multiply a matrix onto a vector, well, actually this time let's just do a little bit of algebraic multiplication. We know that multiplying a matrix onto a sum of vectors, the distributive property holds, so we can multiply a onto each of those, and then the scalars in each of these terms factor out in front. So we'll have x1 a times b1 plus x2 a times b2, and so on through the end. Now, at this last step, you may realize, hey, we've still got those entries of x multiplied onto vectors, and so what this is a matrix times a vector if the vector is the same x we started with, and the columns of this matrix are a times b1, a times b2, and so on, a times bp. Now, hopefully this is familiar to you. This was another way of interpreting the matrix AB, the way that we've defined it. Remember, AB has columns formed by multiplying A onto the first column of B, A onto the second column of B, and so on. And so this motivates why we wanted to define matrix multiplication in this particular way. All right, well, in this video we want to pull in this idea of an inverse matrix. What if the matrix we multiply A by is actually A inverse? Now, pictorially, what we're going to imagine, recalling that A times A inverse is the identity matrix. In either order, when you do that multiplication, you get the identity matrix. And so multiplying both of these vectors onto, both of these matrices onto any vector x should produce the identity times x, which of course is just the vector x. So if my map A, if my multiplication by A produces a map mapping x to ax, then multiplying that quantity by A inverse is supposed to put me back at x. A inverse A is equal to the identity. Multiplying that onto x gives me just x. So now let's go back and remember a few things about linear transformations. We saw this at the very end of chapter 1. You'll remember that a linear transformation was defined as a function that satisfies these two properties. And back at the end of chapter 1, we concluded that actually when you take a matrix multiplied by a vector, if that is your function, t of x is equal to ax, then actually t turns out to be a linear transformation. And then at the very last section of chapter 1, we saw that actually any linear transformation can be written as a matrix times your vector. Okay, so there is a matrix which we call the standard matrix for every linear transformation. And we're going to explore that connection between linear transformations and their matrices in this video, particularly when we talk about inverses. So we have defined what it means for a matrix to have an inverse, but now we're going to talk about what it means for a linear transformation to be invertible. We'll say that a linear transformation T mapping Rn to Rn is invertible if there is another linear transformation S that has the property that when you take S of T of x, you produce back the vector x. So it's kind of like S undid whatever T did and put you back where you started. Similarly, it should be the case that if we were to perform S on x directly, followed by performing T, then the end result should be the vector that you started with. So these two linear transformations in some sense undo each other. If we start with x, we perform T, and then we perform S, we should be back where we started. X should be the result of S of T of x, and vice versa. If that is the case, if there is this linear transformation S having this property, then we will say that S is the inverse of the linear transformation T, and because it's more convenient, we often won't write S, we'll write T inverse instead. So T is a linear transformation, T inverse is the transformation that undoes the action of T. All right, now here is our theorem. We're going to reveal it in a couple of steps. If T is a map from Rn to Rn, if it's a linear transformation, and if we were to let A be the standard matrix for T, so remember what that means. What we're saying is that T of x has the same output as A times x for all x in Rn. So with this setup, transformation T will be invertible. There will be an inverse linear transformation if and only if A, this standard matrix A, is an invertible matrix. In other words, you're going to find a map that undoes the action of T if and only if the matrix A that accomplishes the same effect has an inverse. Now, when that happens, if it is the case that A is an invertible matrix, then the function T inverse of x, which we're going to define by taking the inverse of A and multiplying that onto x, whatever that function is, that will be an inverse linear transformation of A. And to see that, what we can do is take T inverse of T. We know that T of x is supposed to be A times x, and so what T inverse of that turns out to be is just A inverse times AX. And of course, when we multiply these together, the two matrices become multiplied to produce the identity matrix, which when you multiply onto the vector x just gives us the vector x. So these two functions undo each other in that order. They also undo each other for similar reasons in the other order. And so we see that this map, T inverse, which is defined as A inverse times x, is the inverse transformation for the linear transformation T. Okay, as we wrap up here, we have defined what invertible linear transformations are. They're linear transformations that can be undone using another linear transformation, which we're calling T-inverse. And to decide whether a linear transformation is invertible, what you really need to do is talk about whether the standard matrix exists. And what we've said is that the standard matrix for T-inverse should be the inverse matrix for A. So, when we talk about the invertible matrix theorem, having an inverse for your linear transformation depends entirely on everything else in this theorem. A is invertible if and only if the linear transformation T of x is invertible, and that will happen if and only if the linear transformation is 1 to 1, and that will happen if and only if the linear transformation is onto. So these ideas are all connected to each other and all connected to A having an inverse. All right, so as you ponder the results of this last section we'll talk about in Chapter 2, please keep in mind that having an invertible linear transformation corresponds exactly to the matrix involved having an inverse as well. With that, please take a look at these outcomes, and please let me know if you have any questions, and I'll see you in the next video.